Welcome to our ICRA2022 presentation, When Being Soft Makes You Tough, a collision-resilient quadcopter inspired by Arthropods Exoskeletons. It's very unlikely that a robot will always avoid collisions, but nature embraces them, using exoskeletons mixing rigid and soft materials. By embracing collisions, UAVs can reduce control complexity, fly in confined space, do real-world reinforcement learning experiments. Past work strategies were rigid cages or bumpers, rotatory cages, long carbon fiber struts, weight reduction, and few-head truly flexible frames. The problems we found: rigid frames and shafts, hard to manufacture, no flexible exoskeletons, exposed propellers, and no truly autonomous microdrones. Cognifly is small, under 250 grams, mixes flexible and rigid parts, easy to manufacture, capable of autonomous flight, runs complex neural networks. And when we say flexible, we really mean it. All 3D printed parts are small, easy to print, and it uses standard components, easy to find. We supply step-by-step instructions showing how to assemble the printed parts, using carbon fiber rods or even barbecue skewers. And here you see the neural network onboard accelerator. Cognifly was designed to be small, easy to transport. Its battery slides in and out, opening the way for an automatic battery swapping system. It can be easily customized to adapt to very different applications. Everything is available online, open source and free to use. To test our design, we executed crash landing experiments, dropping the UAV from 3 different altitudes, and modeled the system as a simple mass spring damper. Data were collected as accelerations using the ADX-L377 and a custom data logger sampling at 1 kHz. Testing our design, here in red, against a rigid structure, in blue, we achieved an altitude 5 times higher, while the measured peak acceleration was smaller. Our simple model, the blue line, was able to approximate the main behavior of the peak acceleration data collected. The same simple model allowed us to predict the CG displacement and extrapolate to unseen situations like the fall from 262 centimeters. Finally, thanks to the mass spring damper model, we were able to study the energy distribution in our system and forecast how bad an impact can be. Additional experiments helped us to verify that we save weight by having a protective structure that acts like an exoskeleton, sharing the loads with the main frame. This first video shows our UAV falling from 262 centimeters. It bounced, bending its flexible joints, helping it to absorb the impact energy and land without any damage. The second video shows an experiment where 2 UAVs are exploring the environment, avoiding collisions thanks to the Robot Swarm programming language bus. Our last video presents an experiment using our user-friendly Python library to remote control the UAV. This library was specially designed to be used in the classroom with secondary school students. In this example, when the UAV detects a person, it automatically lands. Thank you for watching our presentation.